So just to remind you, the second midterm is next Monday. 30 multiple choice questions, same as usual. Take the old exams, take them, don't look at the answers first. What else? The exam will focus on material since the first midterm, primarily on that since sort of carousels and roller coasters and balls in air is the end. I'll talk about airplanes, I'll get started into airplanes, but I won't, it's not on the exam. What else? I'll have my office hours 9 to 11 on Monday instead of in the afternoon, just so you can come and ask me questions about whatever you like. All right? Any issues regarding the exam, questions about it? Don't bring a bubble sheet, just bring a pencil or something to write with. All right. Where I left off with last time was talking about balls, basically about how air resistance works. And just sort of remind you that the issues, that in principle, if a ball goes very slowly through the air, or the air goes very slowly past the ball, and for real balls, we're talking really slowly, like how your fingernail grows. It's way too slow to be realistic. But at very, very slow speeds, the air will encounter the ball, spread smoothly around it, and then reassemble at the back perfectly. And the streamlines will remain intact the entire way. It's laminar flow the whole way around the ball. And as a result of that, you get a high pressure. There's a high pressure that develops at the front of the ball as the air bends away from the ball. It's pushed away by the high pressure. There's low pressure on the girth of the ball as the air bends toward the ball. It's pulled in by the low pressure, you could think. It's actually pushed in by atmospheric pressure outside, which is higher. And then at the back of the ball, the air is pushed away from the ball to leave. And again, the pressure at the surface of the ball is high, above atmospheric pressure. So that's life for very slow-moving air around a ball. It doesn't happen with real balls. But it does happen with smaller objects like dust particles and germs and so on. I used to smack a couple of chalk erasers together. You can watch the stuff just sort of sit in the air. The dust, it's just a nuisance to have that dust floating around. The dust floats there in the air. It's not literally floating. It's not held up by buoyant forces. It's still, I could go do it. Here, I'll pretend I'll do it. There it is, chalk dust. It's chalk. Chalk's heavy, it's dense. It doesn't float in air. So it would drop like chalk if I dropped it, which is, yeah. And so what's keeping it up there? It's just having a terrible time moving through the air because this flow pattern develops around it. There's no pressure imbalance, it's symmetric pressure-wise, but the rubbing effect of the air going past the ball, the chalk particle. The chalk particle experiences what's known as viscous drag, the drag associated with the rubbing effect of the air around the chalk. And so, yeah, just to do this right, I told you in this very slow-moving air situation, high pressure at the front, high pressure at the back, low pressure all around the girth. It's so symmetric, there's no net pressure force, and that's why we leave that aside. And the only force that's acting on the ball as the air goes by it is a downstream force due to the rubbing effects of viscous interactions, the fluid against the fluid, air against air. All right, but this is what's responsible for the dust floating around the air that you see, or smoke, or the clouds. What keeps the clouds up? They're just tiny particles having a terrible time moving through the air because although they're heavy, they're dense, they can't fall well because they experience such big air resistance. Okay? For realistic balls, that is balls that are where the air is moving by at any reasonable speed, the flow isn't laminar anymore. It starts out, it tries to be laminar. The air encounters the front of the ball, it does bend away from the ball, and that necessitates high pressure at the front. It then tries to bend toward the ball, and that necessitates low pressure around the girth of the ball. And then it tries to go to the back of the ball. And as it does that, it's going from low pressure at the back of the ball to rising pressure behind the ball. And it's being pushed backwards, which slows it down. And if it's got enough forward momentum, it can make it. but the problem is that it rubs as well as not only is it pushed backwards, it's also interacting with the surface with viscous effects. So it slows down, it comes to a stop, and laminar flow just dies. It kills off the beautiful flow of steady state flow, and you end up with turbulence behind the ball. And that turbulence has basically atmospheric pressure, and on average, the air is pretty much moving at the ball's speed now. The ball has dragged the air has dragged the ball. The two have messed each other up badly. And for a ball, if the ball is moving through the air, well, let's leave it with the air going by the ball. As the air comes by the ball, everything was looking nice. It was going to try to get off the back and leave and be essentially undisturbed by the ball except for viscous stuff. Alas, you end up with turbulence behind it. And once the turbulence appears, the air that was flowing by swiftly is not moving very much anymore once it leaves. It's moving approximately at the ball's speed, which in this current, as I'm currently doing it, is motionless. So it basically stops the air. Not completely, but a lot. And so the ball has taken a lot of the momentum out of the air. The air doesn't have it anymore, heading that way. So the ball's got it. So the ball now is being pushed downwind. It's being given momentum by the passing air. Is that okay so far? Questions about that so far? There are details like how big that turbulent wake is important, because if it's small, if for some reason it's small, then the ball isn't stopping as much air, and the drag of forces that result are not so big. I should remind you again of where the actual force comes from. It comes from the fact that there's high pressure in front of the ball and atmospheric pressure behind the ball. Those don't balance, they don't cancel. So there is a net downwind push on the ball due to unbalanced air pressure. And the more that the back of the ball can let the air work its way to the back and produce a small turbulent wake, the more the high pressure does begin to develop on the back of the ball to cancel the backward push from the high pressure at the front of the ball, and the smaller the air resistance. So I'll come to that question in a sec, or a little down the road. Let's see, what do I want to say at this point? About having talked through this, and I did talk yesterday about how you can deliberately shrink the size of the turbulent wake. It's done with, for example, with golf balls, it's done with the dimples. The dimples manage to make the turbulent wake smaller and therefore get a smaller air resistance force. But for some of the practical applications of this whole idea, this applies to balls, but it applies to like everything trying to move through the air. Almost everything has turbulent wakes behind it. And they all develop pressure drag forces as a result. And so how do those, what are the sort of the characteristics of that pressure drag, and how can you deal with it? Well, first off, pressure drag is typically proportional, I should be more specific. The pressure drag force on a ball or anything else, like you running forward or bicycling forward, the pressure drag force on you is roughly proportional to a couple things. How big the wake is in area. That's essentially how much air you're grabbing hold of and dragging with you. So if we look at the size of the wake, so if you can shrink the size of the wake, of course, you're dragging less air, you get a smaller pressure drag force. And so different things, I'm thinking of cars, different vehicles have leave different size wakes behind them. They all leave wakes behind them. With great engineering, you can manage to leave a very small wake behind you. And I'll come to that when I talk about planes. Planes are streamlined. They're designed with great effort to make sure they don't mess up the streamlines to the extent possible. So they leave remarkably small turbulent wakes behind them, given their size. In contrast to that, sort of a worst case scenario is a boxy delivery van. It's just basically a box moving down the road. It leaves a turbulent wake behind it. It's actually bigger in cross section than the van itself. So it's an aerodynamic disaster. terrible, terrible pressure drag. And then there's everything in between. A lot of sports cars are designed, and this is something that I think comes up in the problem set. A lot of sports cars are designed to try to shrink the size of that wake, to keep the air flowing as streamlines as long as possible. And we'll talk in the context of airplanes about what are some of the issues you've got to avoid in order in order to have a laminar flow as long as possible. So pressure drag is proportional to the size of that wake in cross section. The other thing, another thing that's important is how fast you are moving through the air. And pressure drag is proportional to the pressure drag force on you or the ball is roughly proportional to the square of your speed. So you double your speed, you get 4 times the pressure drag. So why that? It's because, just think of the ball, as the ball moves through the air, if you double its speed, it encounters twice as much air every second. It simply just moves, it just bumps into twice as much air. And it ultimately drags twice as much air, it drags twice as much air with it at twice the speed, because it's going twice as fast. So you get a factor of 2, we've doubled the speed. You get a factor of 2 for hitting twice as much air, and you get another factor of 2 for dragging that air twice as fast. So pressure drag is roughly proportional to the square of speed, the power you need to keep moving forward against pressure drag forces has yet another factor of 2 in it. Why? Because if I'm pushing the ball forward against air resistance through the air, if I double the speed, I have to push it 4 times as hard to keep it coasting, to balance the air resistance. Can you follow that idea? You okay with that idea? If I'm keeping it moving forward by pushing it forward with a force that cancels air resistance. If I double my speed, there's 4 times as much force, and I'm traveling twice as far every second against that force. I'm doing 8 times the work every second. 4 times the force and twice the distance. That's the work involved goes up by a factor of 8. Is that okay? So to move, if you're fighting air resistance and nothing else, that's the whole job. This is typically on a bicycle. This would be probably true. On a level ground, the only thing that's keeping you, that's slowing you down, that's preventing you from simply coasting perfectly, is air resistance. So to keep yourself moving forward, if you want to travel twice as fast, all else being equal, you're going to have to provide 8 times as much energy every second, which is 8 times as much power. All right? I'm going to use this as an example. Like, it's been a while since I went swimming over in the AFC or something like that. But there will be people that will go by me twice as fast as I'm going. And it's the same with physics as yours. There's a factor of 8 in power, unless they're just simply leaving smaller wakes, and they're leaving, ultimately, some of it's leaving smaller wakes. It's not that they're 8 times as powerful as I am completely. It's partly that they're just better at minimizing the size of the wake. Same physics, though. If moving through air, moving through water, same problem. Okay? This furthermore explains why boats have great trouble moving faster than, say, 100 miles an hour through water. First of all, they want to minimize the wake. They don't actually want to go through the water anymore. They want to get up above it, so they mostly fly on the water. But for a boat that is going to go through the water, to go twice as fast, they're actually having to crank out 8 times as much power out of the powerhouse or the propeller system to drive it. All right? Other physics issues that you might care about. The idea of drafting. I was talking to somebody before class about this. If you've ever watched a bicycle race, Tour de France type race, a huge fraction of the activity is in following other people and jockeying around so that you're always behind somebody, or unless you're working as a team, a small team trying to keep moving. The biggest energy sap in the whole process is pressure drag, is the air resistance problem. So the person in the front of any pack is experiencing this full pressure drag problem that I've just described. High pressure in front, low pressure on the sides, no pressure, atmospheric pressure behind them. They're fighting the full flow of air coming by them. Somebody who goes into the air pocket behind them, that turbulent wake, that air is moving pretty much at the speed, the forward speed of the person who created it. So the lead bicyclist is dragging the air with him or her, and the person right behind them is moving through air that is itself already moving forward. And you get dramatically less air resistance. So some sports allow drafting, and it becomes like a major issue within the sport. And some forbid it. So that if you're caught drafting, you're eliminated, because it's so important. Is that okay? Any questions about drafting issues in sports? Sometimes there's other cases where drafting is interesting, but it's actually a hazard. The one that comes to mind is, in any given semester, I have some number of people who are skydivers, some of them great enthusiasts of that. So I think one woman who was mild, meek woman who secretly was like a complete enthusiast about skydiving. She was telling me about all the issues that I wouldn't have anticipated. And one of those issues was that skydivers do work hard. Well, they try not to go over one another, because if two skydivers are descending like this, side by side, they are both experiencing tremendous upward pressure drag as the air goes past them. And they eventually descend at a constant velocity, the famous terminal velocity, where their weight downward is exactly canceled by the pressure drag force upward. And so they come down steadily. And if they have, the two of them have to be careful, because if one of them pulls into a tighter shape that cuts through the air better, makes a smaller wake, that person will go faster, have a faster terminal velocity. So it takes some skill to all descend at the same speed. But the other thing is, if one of them goes over the other, the one on top is suddenly drafting the one on the bottom. That is, the one on top is now moving through the air that the one below has already disturbed and is dragging with him or her. And the person on top will suddenly lose air resistance, and terminal velocity will increase, and they'll drop on top of the person below. And she called it a burble, and I just looked up before class, and apparently it is called a burble. You don't go in another person's burble, because you drop on them if you do that. You okay with that? With why that happens? All right. Does pressure drag force always oppose velocity? It always opposes velocity through the air. So that if the air is stationary and I'm moving through the air, we now know that my velocity relative to the air is very simple. It's exactly to the right. Pressure drag is always exactly opposite. It's always downwind. It's always, in this case, would be to your left. If the air is moving and I'm moving, now you have to compensate a bit. You have to figure out what's my velocity through the air, not relative to the seats, but relative to the air. And again, it's always exactly downwind, by definition. Forces that are not downwind, but rather are directly to the side, are called lift forces. And things that are at awkward angles in between are combinations of lift forces and drag forces. Is that okay? One question came in about the Hyperloop idea, with this idea of making a pipe, taking out some good fraction of the air out of it, and then just sending a vehicle through it much faster. And yeah, you can, by reducing the mass of the air, by going to low pressure, there's less density there. And so the vehicle will still drag air with it. However, it's dragging less mass with it, so the forces involved are smaller, because the air is just thinner. And in principle, if the air goes in a full vacuum, there's no air resistance at all. So you can reduce air resistance by going to lower pressures. And finally, that's important, for example, for planes that fly at high altitude. There's an advantage to flying at high altitudes. They're going through air that's less dense, and so any air they drag with them sucks less momentum out of them. So that's a great advantage. The disadvantage, though, is, as we'll see, planes keep themselves aloft by pushing on the air. And if the air gets thinner, less dense, that becomes trickier. And so how do they manage to push on enough air that they're going to throw it downward? That's the secret. the preview and everything else is details. They throw the air downward. A plane throws it downward and manages, as a result, to get rid of all the momentum, the downward momentum that's given to it by gravity. So it accumulates no downward momentum, and it zooms along level. To get enough, to throw down enough mass every second to get rid of their seconds worth of momentum from gravity, they have to encounter a lot of air, a lot of air mass. Down near sea level, that's easy because the air is denser. Way up high, not so dense. How do you compensate? Go fast. If you go, a plane that goes fast enough encounters a lot of air anyway, just by virtue of its speed. And so jets and high-speed planes can fly fine at 30, 40,000 feet. Propeller planes much more problematic, in part because, well, how they spin their propellers is another issue, but they got to be able to go fast enough to encounter enough air. Okay? What else did I want to say about air resistance? Do you have guys have any questions about air resistance stuff? Things that, air resistance, water resistance. In any case, I hope you will pay attention to air resistance in the future, to sort of watch it happen and the little issues with it. And the turbulent wakes that are left behind, you can see them now being an autumn day with leaves everywhere. You watch the leaves behind a car. Another example of air resistance being interesting and useful is that they clean up the leaves around here with air blowers, right? They blow this thing, but with a proper hose on the end. What is moving the leaves? It's all pressure drag. High pressure in front, turbulent air pocket behind, the air gets blown along. A couple thoughts about the flow around the sides of balls too. You'll have to deal with some of this for the problem set that's due on a week from today. But the fact that the air comes along, encounters the front, develops high pressure there. As it goes around the side, it develops low pressure. That low pressure has interesting effects on things. Well, on the ball, it's not so obvious that there's anything going on. But in certain circumstances, it is obvious. Like if you're walking with an umbrella, it being a rainy day, this is relevant. If you hold the umbrella exactly vertical, it's kind of like the top half of the ball. And as the wind blows across the top part, let's not worry about below it. As it goes over the top part, the air has to bend toward the top of the umbrella to follow its curve. And that means it's bending toward the umbrella. It has to have lower pressure near the top of the umbrella compared to far from the top of the umbrella. There's low pressure on top of the umbrella that is lower than atmospheric. And inside the umbrella, it's basically atmospheric pressure, just the air just sort of sitting around there with your head in it, perhaps. And that means there's a pressure imbalance across the skin of the umbrella, and it's an upward pressure imbalance. And you've surely had that feeling where the umbrella is going to sort of lift off Mary Poppins-like and suck out of your hand, right? This is where that comes from. It's that bend toward the surface. A case where this matters more than just fun and games with an umbrella is in your house. Having had a bad hurricane season this year, one of the ways in which houses are damaged is when the air blows across, up and over a peaked roof, traditional peaked roof. That bend, it's not that different from having a big umbrella there. Low pressure develops above the roof relative to the air in the attic, and the roof can get lifted right off the house. So that's how people lose their roofs, is the drop in pressure that comes as the air bends over the top. And properly built houses should have the roofs strapped down against this problem. It seems like impossible. The roof is very heavy, and you should only worry about having it supported. Who cares about lifting it up? No one's ever going to lift it up. So you can imagine houses being built with a roof just sort of set in place by weight alone. Bad idea, because if you get a big wind, it'll just lift off. All right? I think I'm out of things to say. Oh. I'm getting questions there. Are all objects moving opposite the air experiencing pressure drag forces unless they're tiny enough that they don't leave a turbulent wake? The answer is yes. So virtually anything of decent size moving through the air faster than a snail's pace is experiencing pressure drag. It's being blown downwind. Of course, the force depends on the square of the speed, so if it's going at 2 snails' pace, you know, it's not going to have much pressure drag, but it'll have a turbulent wake behind it nonetheless. It'll just be not very significant. So the only things that realistically experience viscous drag alone are the tiny stuff, the dust, the ash, the smoke, bugs. Actually, not insect bugs. They're probably turbulent too. Germs. All right. And what's the difference between the factor of 16 with the pressure factor of 8? There was a factor of 16 that showed up in what's called Poissons Law. If you looked at the flow of water through a pipe, so that was the context. The water flowing through a hose, the amount of water you get through, given a certain starting pressure and a certain ending pressure, and a certain length of the pipe, is proportional to the 4th power of the diameter of the pipe. Partly because of the cross-sectional area of the pipe gets bigger. You know, double the diameter of the pipe, you got a lot more opening to go through. That's 2 factors of the diameter. And then 2 more by getting the water away from the walls. The center, the sweet spot inside a hose is the center. That's where the water goes the fastest. And so doubling the diameter of the hose allows you to put a whole lot more water through, 16 times as much. And this is why firefighters use hoses like this. They may still send it out of a small nozzle, but they want that easy flow. Okay? Yeah, Proud? What? Why? The midline. Yeah. So the question is, as the air flows around the midline of the ball, and I don't know what to call it. It's this entire region around the ball like that. That air approaches this point heading toward you guys, away from the ball. And if it did, it would continue away from the ball, it would leave an empty space back here. And the air rubbing against the air forbids that from happening. It will pull the airflow toward the ball. But for that to happen, low pressure has to develop here. The low pressure here doesn't attract the flow, but it does not fight hard against the air far away. So the air far away shoves the flow against the ball. Is that okay? So the air here is arcing toward the ball. It has low pressure on the inside of the turn, lower than outside, which is atmospheric. And the air actually is traveling, I should also say, quite fast there, faster than anywhere else in the flow. It has converted pressure potential energy that was present here into kinetic energy here to move fast. So this is low pressure air, and it's also high speed air. And again, I think I mentioned last time that this truism around that high speed air is always low pressure air. No, the context matters. That's only true if you're watching the air flow along a streamline and you're saying the air has sped up. It's high speed now because it used to be low speed. Now it's high speed. It got the energy from somewhere. Where did it get from? From its pressure. It's lost pressure. My example of high-speed air that is not low pressure is just a fire, with a carbon dioxide fire extinguisher. You throw it out of an airplane. It's very high-speed air, well, carbon dioxide, and then the pressure's plenty high. So that's a counterexample where the context is wrong. That has nothing to do with the flow. All right. Okay? Other questions? Yeah, they're coming in like popcorn. All right. Can I explain the difference between viscous drag and pressure drag? Sure. The viscous drag, which is always present in all my stories, whenever air moves past an object, no matter how big or small or fast or slow, it's always rubbing by way of viscous drag. That is, there's an interaction between the air and the surface, some interaction, they're rubbing a little bit at least, and so the ball experiences, whatever, the object experiences some push downstream, downwind, which is a drag force, and because it's due to viscosity, it's a viscous drag force. And I think viscous drag forces are proportional to speed, not speed squared, speed. If I'm wrong, I'm wrong, okay? Pressure drag is different. It's an extra bonus drag force that shows up when the air goes turbulent behind the object. And it goes turbulent because the flow fails to go from low pressure on the sides to high pressure on the back. It comes to a stop, breaks off the flow, and creates a turbulent air pocket. And in that case, the drag force is called pressure drag because it is accompanied by unbalanced pressures. It's actually caused by unbalanced pressures around the object that have a net effect of pushing the object downwind. And it's proportional to speed squared. Is that okay? Can I explain the pressure difference in a bend in a hose? So this bend, the bend I've talked about in the ball, where the air bends away from the surface initially, involves a pressure gradient between high pressure near the ball and atmospheric pressure, which is lower, away from the ball. That causes the bend. And then there's a bend here that's caused by low pressure near the ball and atmospheric pressure far from the ball, which is a net push toward the ball, bends in. And then ideally it bends away there, but usually get at a mess. In a hose, you have the same kind of bends. When water or air, anything is going through a hose, it could be an air duct, and you force it to bend like that. You force the airflow to bend, it's going to have, the air is going to bend because of a pressure gradient. Something pushed on it. The air in the middle, it's not touching anything. It's only touching other air. So it must have been pushed by the air itself. So if it's bending upward, then it must be being pushed upward by an imbalance in pressure between lower pressure below it and higher pressure above it, just pushing it. So you get these funny pressure imbalances. Let me show you that picture of, I find it, garden watering. I do it, I did it. Now I gotta dim the lights. The pressure, oops, don't do that. Operator insanity here. So, as this is water flowing, we're looking down on it really, but anyway, it's flowing as we see it upward and arcing around to the right. That arc is caused by a pressure gradient in the bend. And it's bending toward the lower pressure, so the lower pressure has to be on the inside of the bend. The center is about here, so it's bending towards the green dot. And it's being pushed by higher pressure at the outside of the bend, pushing inward. All right? And accompanying the low pressure on the inside is an increase in speed. So that's actually high-speed water. That water is flowing faster than anywhere else in the drawing. If you just measure its speed, it's got more kinetic energy and more speed. There on the outside, the water is kind of moving slowly. It's slowed down to build up its pressure. Another detail just to bring up here is if a hose is getting old and if it bursts because the flow through it just finally it gives out, it will typically burst on the outside of a turn because that's where the pressure is highest, regardless of what the ambient pressure is, the average pressure is. The highest pressure is on the outside of the turn. Okay? And alas, this is true of people too, that the outsides of our plumbing, arteries and stuff, they're particularly stressed and in danger of rupturing on the outside of turns. So, periodically, people have artery disasters, and it's typically the outside of the turn, the outside of a bend in aorta or something that's affected. Is that okay? Wow, lots of questions. Good. I appreciate the questions. A question looking back at buoyancy. So let me go back to that. This whole story lives on top of the world of buoyancy, the airflows and stuff like that. Buoyancy is also an issue, and they're both present at the same time. So this ball is experiencing, right now, as the wind goes by it or as it moves through the wind, it's experiencing a downwind pressure force. It's also experiencing a vertically upward buoyant force. Not enough to lift it off the ground, but enough to give it it falls pretty slowly, in part because of air resistance and in part because the buoyancy is canceling a lot of its weight. So the question is, the buoyant force that we're seeing here on Earth is due to gravity packing the air more tightly down below than it is up above, because the air down here is supporting the weight of all that air, and the air up here isn't supporting as much weight because it's got stuff below it, which doesn't count. So the buoyant force comes about because of higher pressure and density down here than up here due to gravity. So far, so good? So the question is asking about, I asked you in the problem set, if you remember. I hope you know. In a spaceship way out in the boonies, no gravity. When they accelerate forward, what happens to the various balloons? Helium and air. And the answer, just to tell you, the answer is the air-filled balloon appears to drift towards the back of the, it does drift toward the back of the ship. And the helium balloon squirts toward the front. And that comes about because in the accelerating ship, a buoyant force develops. Why? Because the air which has mass associated with its density, the air wants to keep doing what it's doing, and the ship overtakes it. The ship, let's say it's accelerating to the right. The ship is, as it accelerates to the right, the air, if nothing pushed the air forward, it would just stay where it was and slam into the back of the ship. Well, briefly, that kind of thing starts to happen, but very soon the air develops a pressure gradient between high pressure at the back of the ship and low pressure at the front of the ship. And it's that pressure gradient that pushes the air forward to make it accelerate with the ship, so you don't leave it behind. Well, that pressure gradient creates a buoyant force. It pushes anything in the ship's air forward. It pushes just hard enough to make the ship's air itself move forward. So if you put a balloon in there that is heavier than the air it displaces, that balloon will be pushed forward, but not enough to make it accelerate forward with the ship. And it will therefore drift toward the back of the ship. If you put something in the air that has less mass than the air it displaces, it'll accelerate extra fast, and it'll squirt towards the front of the ship. And you don't have to go to space to see this effect. Just get some balloons. I should film this sometime. Get some balloons and go for a ride in a car. And if you put air-filled balloons in the car and you put helium-filled balloons in the car, they'll go in opposite directions when you start forward at a light. When you accelerate forward, get a good car, a Tesla in ludicrous mode, okay? You accelerate forward fast, a big buoyant force will develop in the car, pushing forward on everything. The air-filled balloon, that force won't be enough. The balloon will drift toward the back of the car, just like a bowling ball. Obviously, we drift toward the back of the car. The helium-filled balloons will squirt towards the front of the car. And this is familiar to parents who have had kids with helium balloons in the car and sort of lost interest in them, and they're just sitting on the roof of the car, just bouncing around. You head forward to the light, and the helium balloons squirt toward the front of the car. Is this okay? Watch next time you're in a car-filled balloon, balloon-filled car. Watch them happen. All right. Can I explain the diagram on the projector? This diagram, is this the one that we were talking about? Water flowing around the pipe like this. This is the inside of the turn. And like everything else, if this were a track and there were runners on it, in order for them to go around that turn, they'd have to be pushed toward the center of the turn. With runners, it would be the ground doing the pushing. In this case, because it's fluid, there's no ground there. The fluid has to be pushed toward the center turn by what? By a difference in pressure between high pressure on the outside of the turn and low pressure on the inside. Is that okay? Posting explanations to the answers in the old exams, that's a work in progress my whole life. I never managed to get sometimes I manage to get ahead and do that, but I run out of time all the time. So the answer is probably no. Ask me questions at my office hours. Okay? Does pressure drag occur only in turbulent airflow? Yes. It's a result of the turbulent airflow. You lose the otherwise perfect cancellation. Some of the old exam questions asked about centrifuge with blood and its pressure. Centrifuge is very much related to this. Centrifuge, those of you who've never encountered one, they're very useful for separating things that are high density and low density. And blood, for example, or chemicals, or there are pumps that are based on this idea. When you when you go around a corner like this, a pressure imbalance develops between high pressure and low pressure, right? Well, if you keep going around that curve over and over again, now you've got a centrifuge. And the material, the fluid is traveling endlessly around in a circle, always accelerating toward the center, and it's always pushed toward the center by a difference in pressure, by differences in pressure, a pressure gradient. You can kind of think of there being a buoyant force towards the center, because it's this constant inward acceleration. It's a lot like a car. If you got a car and you just drive around a circle all day doing donuts in the parking lot, the air-filled balloon, a pressure gradient will develop in the car between high pressure on the outside of the turn and low pressure on the inside as you go around. And the air-filled balloons will drift towards the outside of the outside side of the car. Another thing to film, someday when I got an empty parking lot and I'm not worried about getting arrested for driving around in circles with a camera in my hand. Okay, so the air-filled balloon will go to the outside because the buoyant force that's developed because of this inward acceleration won't be strong enough to bend the air-filled balloon's path. The helium balloon will go to the inside because it's light and fluffy enough. It's got low enough mass and low enough density to go to the inside. So that's what a centrifuge is doing. It's whipping a liquid around in a circle. The same idea, a buoyant force develops, pushing all the liquid toward the center, but certain parts of the liquid will manage to actually make progress toward the center, and the denser parts, they're too heavy. They don't displace enough liquid to make up for their own mass, and so they go to the outside. So it's good. It separates stuff into the high density and low density. Remember, density is mass per volume. Is that okay? Same physics. In the balloon and car scenario, is the front or back of the car at high pressure? If you accelerate forward, the air has to be pushed forward to stay with the car. So it needs a higher pressure in back to give an overall forward push. So you can figure this out yourself. I'm telling you, but you should be able to figure it out yourself down the road once you understand the idea. Can I give you all A's? Yes. I shouldn't say it. I'll say it. If they ever get around to allowing open carry in classrooms, everybody gets A's. Once in my life, I've had a student try to beat me up in my office, and I survived that one. I don't ever want to do that again, and certainly I wouldn't want to do it with weapons involved. All right, let me finish up talking about balls in air on a different note here. I got one last, okay, so airplanes will come to, maybe not today. The balls that I've talked about up to this point, the ball is just not turning. It's just a sphere that's just hanging in there, and the air goes around it, and it experiences either viscous or viscous and pressure drag. If the ball is spinning, life gets more complicated and interesting. If the ball is spinning, let me do the spin I've got on one of my drawings. The drawing that's up there. The spin I've got is this spin. So if the ball is moving, is this right? No, it's this one. So the ball is moving through the air, spinning like this. The air that's going over the top is moving with the ball. The ball's top skin is moving with the air. Let me go back and rewind and start over here. As the air is coming at us, and I move the top skin of the ball with that air is being assisted in its flow around the ball. So the bottom line is the air coming over the top of the ball with that spin is flowing more easily over the top of the ball, and it hangs onto the ball longer. And when it leaves, as streamlined still, it leaves heading downward. It doesn't leave halfway, at the midpoint of the ball anymore horizontally. It actually it follows too far. And the air that's moving under the ball is being fought by the ball. The ball's coming at that air and rubbing extra hard and causing trouble. So the airflow becomes asymmetric, top and bottom. And just to show you the drawing of this, a drawing. Here's that airflow rushing along. It goes over the top and sticks around too long. And it goes under and sticks around too short. And the flow leaves heading deflected downward. The fact that the air is deflected downward, that flow is deflected downward, already implies that the ball has pushed downward on the air to give it downward momentum. And consequently, the air is pushed up on the ball to give it upward momentum. So that ball experiences an upward force due to pressure effects. The pressure is not even around the ball anymore. And it's an upward force. It's actually up and back, which is an interesting detail. This force is known as the Magnus Force, and it's given all the credit for curve balls and everything else. This is the physics behind curve balls and a lot of other ball effects. There's a second component to that force, which is involved with the turbulent wake. That really the flows behind balls are never laminar. They're always turbulent. So the Magnus Force is not the whole story. There's a wake there as well, and the wake itself is also deflected downward in the story. So rather than sit there on those, if I throw the ball with backspin, so giving it backspin is doing, I'll do it the same way I was doing earlier. If I pull the ball back like this and make it go forward, it will have backspin, the spin I just talked about. And the forces on it, both the Magnus Force and the wake deflection force, are both essentially upward. And they will support its weight to some extent. Assisted by the buoyant force, the forces could pretty much cancel weight, potentially, or even over-cancel it, in which case the ball will arc upward. And if I do this right, I can get the ball to arc upward due to the Magnus and wake forces. I'll try it, and then I'll use the gadgets that help. It certainly hung in the air way too long. That ball should not have gone horizontally that way. This is how a golf ball flies. A golf ball has tremendous back. That one actually arced upward. A golf ball is spinning with that backspin, and it arcs upward. And it's effectively flying through the air. It goes way farther than it would without air. The air is helping it travel. All right? These guys should allow me to give even more backspin. So this is kind of the physics behind it. Certainly golf balls flying. A pitched ball, if a baseball, a pitcher typically pulls back on the top of the ball and also gives it backspin, where backspin is defined as the top of the ball coming back toward the person who threw it. So a ball thrown with backspin experiences enough an upward force due to this deflection of air that it doesn't fall in the arc of a falling ball. It goes too far for that. So it sort of hangs there a little bit. It's not described, the names are important to the people who play these sports. It's apparently not called a hanging fastball, but a ball that's thrown without that spin is called a sinking fastball because it doesn't have that hanging effect. All right? And if you pull back or spin on some other direction, you have a different part of the ball coming back at you, these two forces, Magnus and wake, act at some cockeyed angle or even downward. In tennis, for those of you who are good tennis players, myself not being one, if you want to get the ball to go over the net and very fast, if it goes over slow, it's going to arc down, it'll hit legally within the court. But if you wanted to go over there at lightning speed, clear the net, and still hit in, you want the ball to curve downward. You want it to clear the net and then arc down. You want the air to help you. So they put top spin on the ball, the reverse of what I've just described. Instead of pulling the top back at you, you push the top forward. Give it spin where the top is heading faster, the fastest thing heading forward. And that ball arcs downward because of aerodynamic forces. And it dives into the court. Is that okay? All right. With that, I think I've exhausted the hour. So this is the story of curve balls and the story of balls in air and everything else moving through the air.